The answer is here is true because tempered martensite is a better toughness since we decrease the brittleness of the material. Okay, so option B is done. The hardness of the tempered martensite can be lower than that of the normalized steel. Normalized steel they are talking about. The hardness or it can be lower. It just depend upon. It can be lower. They are telling can be lower, so yeah, it's true because it depend upon the transformation temperature, tempering temperature. Okay, let's move ahead. Both temperature and the time affect the final product of the tempered steel. Is it true? See, in the Martin-City transformation, we said that time and temperature, among time and temperature, only temperature was the one playing the role. While for the while for the tempered steel, when the tempering has been done, the time and the temperature both will play the role. So both temperature and the time affect the final property of the material. So it is true. If we hold for a particular temperature for more time, more particular this particular reaction will take place. While if we hold for the less temperature, sorry, while if we hold for the same temperature but less time, this time, so the extent of the reaction will be low. So comparatively, this phase formation will be low. This is a brittle. So if this product reaction is not taking place that much, so the entire property of the material will be the brittle. Okay, and so that's how it is. Similarly, one can comment for the temperature also, keeping the time to be constant. Let's move ahead to the final question. Tempering completely eliminate all the hardness gained from the quenching. It's not the case. This is false. Completely eliminate? No. It can eliminate to certain extent, but cannot entirely. That's good. So it's false, yeah. So false, true, 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 and false. Okay. Question number 7 is over. Let's move ahead. The question number 8. It's a fill in the blanks type. Let's do let's do one by one. The process of heating steel to form austenite before quenching is called as. The process of heating steel to form austenite before quenching is called austenizing. Perfect. Let's move ahead. Tempering transform martensite into dash plus dash phase. Which are the two phases which will transform? Like martensite. So we are doing the tempering. We have martensite. So now it will transform to which are the two phases? We know in the last question only we saw that. Yeah, alpha pyrite and cementite. Let's move ahead. The two main variable in the tempering are, which are the two variable in the tempering? Like which can be which can affect the property of the tempering? Which are the two variables that can affect the property of the tempering? So more or less we can see that we are following the previous question. Yeah, that's right. So here also we have saw that the time and the temperature will affect. So you have also written that it's a time and temperature. Final one. Higher tempering temperature and longer time result in dash hardness and the dash ductility. Whether it's increase, decrease, or decrease, increase, or both will decrease. Higher tempering temperature. So tempering temperature is high. So what will happen? The martensite to the ferrite and cementite. This transformation will be more. Like this reaction will occur more because the temperature is high. So since this reaction is taking place more and more, so what is mean that the brittle phase is decreasing. Since the brittle thing is decreasing, it means that the temperature, so the hardness will decrease. Hardness will decrease. So since hardness is decreasing, so ductility will increase. So yeah, that's right, perfect. So decrease in the hardness and increase in ductility. That's good. Same thing we will say if we say that high temperature and long time. Okay, so the thing will be reversed if we go for the low temperature and the less number of time, amount of time is decreased. Let's move ahead. Let's go to the question number 9. It's very easy. Tempered martensite consists of what? Alternating plate of ferrite and cementite, fine particle of cementite in the ferrite matrix, BCT, or the pure ferrite. Very good. Option B is the right answer. It's a fine particle of the cementite in ferrite matrix. Alternating plate, this we saw that it will be produced in the perlite. BCT, it is a martensite, as quench martensite. Pure ferrite, that this one we will get when the carbon concentration is very low. Let's move ahead to the next question. Question number 10. Yeah. Match the pair type. A volume change during the transformation. So the volume change during the transformation, option C is the right answer. Yes, perfect. Because FCC is a close pack, BCT is not that close pack as FCC. So their volume change will be there. BCT will have higher volume. So option C is the right answer over here. Surface cooling rate. Surface cooling rate of it's A, yeah, faster than the core. Core cooling rate will be slower than the surface. Oh, I messed up here. Okay. And core cooling rate will be the slower. And the residual stress formation, it's always that result in the tensile stress as the surface. So the fourth one is going to match with the B. Okay, very good. So we have solved these questions. Let's move ahead to the question number 11. We have a lot of questions today because the things are like the amount of content was too much. What is the primary purpose of the mark quenching and mark tempering? Why we are doing this? Why don't we directly quench it? And why we are going for the mark quenching and mark tempering? Also to minimize the residual stress and the quench crack. Perfect. By this process, we can decrease the temperature difference between the surface and the core. So this difference can be minimized. We can reduce this, and which will result in the better like lowering of the residual stresses. Okay, let's move ahead to the question number 12. In mark quenching, the quench is interrupted at what temperature range? Below martensite finish, between martensite start and finish, above martensite but below the nose, above the eutectoid temperature. What do you think? At what temperature we are holding in the mark quenching process? So we know that if this is my TTT curve, that's right, option C is the right answer. Very good. So I'm holding it just above the martensite start, but below the nose. So the process is somewhat going like this, and then we are holding. So this is the process. And after that, then again we will quench, we will cool it. Question number 12 is over. Question number 13. Now match the pair. First one, conventional quenching, mark quenching and tempering. Let's see what answer we will get. It's again more than one can be the right one. So conventional quenching, produce martensite with a high residual stress, perform after martensite formation rapid cooling to the room temperature, interrupt quenching. So conventional quenching we are talking about, yeah, it will produce the high residual stresses, yeah. It will produce martensite with high residual stress. Anything else is there? A rapid cooling to room temperature. Yeah, very good. Option C is the right answer. Now let's talk about the mark quenching. Perform after martensite formation, interrupt quenching above MS, improve toughness of the martensite, allow temperature equalization. So which one will be the right answer over here? We know mark quenching will, it is like D, yeah, perfect, D and F. Temperature equalization is taking place and it's like interrupted quenching just above the MS. Option 3 for tempering. Now the tempering is something B and E. Okay, perfect. It is performed after martensite formation and it improve the, this is over, and it will improve the toughness of the martensite. So option D, option B and okay, very good. Let's move ahead to the question number 14. It's a true and false based. Yeah. Mark quenching eliminate the need for the subsequent tempering. Is it? Since we are doing mark quenching, so we don't need to do the tempering, is it? Actually, it's not. By mark quenching, what we are producing martensite only. And martensite is brittle. So we have to transform, we have to convert this brittle phase. So for that, tempering is needed. Mark quenching is what mark quenching is doing. It's just eliminating that quench cracks, that thermal crack which are there. But the tempering still need to be done. So the right answer is false. Okay, I hope it's clear. Let's move ahead. The cooling rate after temperature equalization in mark quenching must be very rapid. Is it? Must be. False. It can be slow also, like, right? So it's a false. See, the residual stresses are reduced because the entire component transformed to the martensite more uniformly. True or false? Residual stresses are decreases. The reason is that entire component transformed to the martensite more uniformly. So yeah, it is true because now not residual stresses are decreased because the core and the surface region, they are having more or less uniform temperature because we perform the mark quenching. Yeah, first of all, let's say let me tell that this is more or less we are talking about the mark quenching only. So like the answer is true. Let's move ahead. Mark tempering is a technically more accurate than the mark quenching. What do you think? Actually, it is incorrect. Like, it's not incorrect, but technically more correct term we can say that the mark quenching will be, not mark tempering, because there is no tempering involved over here in this particular entire process. So it's false. It's the other way around. If they exchange their position over here, then the answer will be true. The final one, the quenchant bath temperature in mark quenching must be carefully controlled between the MS and MF. Quenchant bath, is it false? Yeah, very good. This is false. We have to control it just above the martensite start. So all this has been done. False, false, true, false, and then again false. Very good. Let's move ahead to the next question. Question number 15. Below the nose temperature in hypo and hyper-eutectoid steel, projectile phase form first. So they are talking about the both hypo or hyper. You can take any of them and answer. Like, you can consider any of them. Below the nose temperature, only benite form, martensite forms immediately, perlite form rapidly. What do you think? So they are talking, option B is the right answer. Yeah, perfect. Because benite formation will take place in both the cases. The benite formation is, we can say, the hypo, hyper, and eutectoid steel. For all three of them, below the nose temperature, only the benite formation is taking place. Option B is the right answer. Let's go ahead. 14, 15. The A3 temperature in TTT diagram represent A3 temperature. What is A3 temperature? We are aware about this particular diagram, right? So now this is A1, this is A3, this is ACM. Okay. So now A3, here is a austenite, ferrite. So austenite plus ferrite, it will be there. So now, so A3 temperature is the temperature where austenite is converting to the ferrite. So what will be the right answer? The start of the pearlite formation, the boundary between the ferrite and cementite region. That's right. This is the boundary between the austenite. Sorry, the boundary between the austenite and austenite plus ferrite region. So option B is the right answer. Very good. Yeah, 32. Yeah, option B is the right answer. 16. Let's move ahead. Question number 17. Why do alloying elements slow down the transformation in the steel? We added the alloying elements. So instead of transformation, it was supposed to be like this, while the transformation is taking place something like this. So it shifted the nose. So why it is happening? They are substituted solid with the slow diffusion. Very good. Yes, Milady, that's option B is the right answer. Okay, let's move ahead. Question number 16. Let's do one by one. Alloying element causes C curve to shift to the dash in TTT diagram. Right, perfect. So the right answer is this one. Let's move ahead. The common alloying element like chromium and molybdenum are that solid in the steel, interstitial or substitution. We can always refer first one to be the A, second one to be the B, and we can answer, yeah, it's a B, substitution. In a plain carbon steel, bainite dash be produced by continuous cooling. Can or cannot? That is A or B. So in the plain carbon steel, bainite can be produced by continuous cooling. We know it is not possible, right? Like plain carbon steel means we not added any alloying element in that. So in that case, what is happening? If I do continuous cooling from any temperature, what will happen that I will always cross this perlite phase. So it cannot be like you can produce bainite 100%. So it cannot be. While in the case of alloying steel, alloy, what is happening that it's something like this. So in that case, if I do continuous cooling, the perlite have the different nose and the bainite has a different nose. So in that case, if instead of plain carbon steel, it's a alloy steel, then the answer will be the can be produced by continuous cooling. Let's move ahead. The dash the quenching rate need to form martensite, the higher the hardenability. Faster quenching rate or slower quenching rate for the hardenability? Which one is required? B. Slower quenching rate. Right. Slower the quenching rate, like more is a nose is far, slower the quenching rate instead of like let's say this is my thing, this is the nose. Option A is like this, option B is like this. So in which case we will get more hardenability is option B, because in this case the core and the surface, the temperature will be, the difference between them will be minimized. So the option B is the right answer, slower. Hardenability is specifically, hardenability is specifically about the formation of dash during the quenching. Austenite or martensite? Option B, martensite. Very good. So with that we have solved this question number 18. Let's move ahead to the next question. Yeah, so here there are the different terms, hardness, hardenability, quenching, and alloying elements are there. We have to match with their description. Okay, so hardness, we are telling that it's measure using the Brinell or Rockwell test. That's right. And A, measure of the resistance to the indentation. That is also correct. A and E. Perfect. Hardenability. Second one. It's a C, ease of martensite formation. Perfect. Yeah, option C is the right answer. Quenching. Third one. It will match with the fast cooling to form martensite. Yeah, perfect. Option B is the right answer. So it can match with the alloying element. Only the D is left, and that's right. Typically increase hardenability, except in the case of cobalt. So here we can say option D is the right answer. Okay, perfect. Let's move ahead to the next question. Again, true and false based. The plain carbon steel generally have the higher hardenability than the alloy steel. What is your opinion on this? True or false? The plain carbon steel has the higher hardenability than the alloy steel. See, plain carbon steel, the C curve will be like this. This is plain. While for the alloy steel, the C curve will look like this. So here we can say that if I have to produce the martensite, in the plain carbon steel, my cooling rate will be this. While for the alloy steel, the cooling rate will be this. So now in which case I can get a more hardenability? In the case of, we can say that alloy steel, right? The plain carbon steel have generally higher hardenability. It's a false. Very good. The next one, the concept of hardenability apply to all metallic material. Is it? Can we apply to the all the metallic material? The hardenability concept? The answer is false over here. It is only limited to the steel when we are talking about the martinsity transformations and all. The steel with a higher hardenability can form martensite at slower cooling rate. The steel with a higher hardenability, yeah, true, very good. Hardness and hardenability are interchangeable term. Can we use it like in place of hardness? Can I use hardenability? Perfect. It's false. Oh, okay, this is over. So false, false, true. False. Let's move ahead to the next question. Question number 21. Yeah. Okay, so our that part is over. The phase diagram, the and the heat treatment part is over. Now we are moving toward the this mechanical strength part. Okay. So now let's go ahead with the first one, the yield strength. So yield strength is a resistance to the elastic deformation, plastic deformation. What do you think? And energy absorbed before fracture, maximum stress before necking. Yield strength is a stress at onset of the plastic deformation, right? So it's option C is the right answer. First one, C. Young modulus is the resistance to the elastic deformation ability to undergo plastic deformation. And maximum stress before necking. Oh, I think I made some mistake. No, it's right, perfect. So question is perfect, I think. Yeah, right. So young modulus, resistance to the elastic deformation. Yes, so that this is going to match with the option A, because we know that if more is my young, this is my young modulus, this is my second young modulus. Case 1, case 2. In the case 2, my young modulus is more than case 1. What is telling that? Like it required more stress just to perform the small deformation, while here it's other way around. So it's a resistance to the elastic deformation. Toughness, energy absorbed, yeah, perfect, energy absorbed before fracture. What about ductility? B, perfect. So more is a ductility, it's easy to deform. Plastic deformation will be very easy, right? So with that we have solved this. Okay, I not wrote third one is D, fourth one is B. Okay, let's move ahead. Next question. True and false based. Engineering stress consider the changing cross-section area during the deformation. Does it consider the changing cross-section area? True or false? Like the instantaneous area, they are telling that in the engineering stress, we consider the instantaneous cross-section area. Perfect, it's a false. The elastic deformation is fully recoverable upon unloading. Elastic deformation is fully recoverable upon the unloading. Perfect, true. It will regain its shape. Ultimate tensile strength is always higher than the yield strength. UTS is always higher than the yield strength. This is again true, perfect. The toughness is a measure in the Pascal. Is it? What is the definition of the toughness? Is that the energy absorbed for the process, right? So energy absorbed we cannot write in the Pascal, right? So it's a joule per. Instead of writing Newton per meter square, we'll give one more dimension, we'll multiply numerator and denominator by meter again, and we'll convert this force into displacement is nothing but a work, which is joule. So this is false. Now one can like debate on this, that both are same, but we have to think from the perspective that what this particular thing want to tell. It's telling that the energy absorbed, right? So we'll put the energy term here. Ductility can be measured by strain at fracture point. True or false? So ductility, what is ductility is that how much deformation has been taken place uh, till the point our material got fractured. So ductility can be measured by strain at the fracture point, that is true. The plastic deformation typically change the crystal structure of the material. The crystal structure they are talking about, FCC, BCC, those things we have discussed. False. Perfect. The extra diffraction pattern remain identical before and after the plastic deformation. Before and after plastic deformation, it is the XRD pattern will remain same. True. Perfect. So false, true, true, false, true, false, and true. Okay, let's move ahead. Few more questions are left. Not so many. When a metal is plastically deformed and then unloaded, the unloading curve is parallel to the initial elastic portion. Curve downward, horizontal, vertical. Perfect. Option A is the right answer. It will be parallel to the elastic portion. Question number 24. What microstructure feature appear in the deformed metal that support the slip mechanism? What feature appeared? Is it that new grain boundary form, slip line within the grain, phase separation, twinning region? So we know that if I have a material which is not deformed, while if I take another material which is deformed now, the same one, here what will happen, that new lines will form. They are telling about the slip line. They known as the slip line within the grain. It's not the option D. Twinning, not the twinning. It's the option B. Okay. So these steps in the crystals which has been formed is due to the slip line. The slip line is the one which is telling about the slip mechanism. Okay, very good. Let's move ahead to the next question. Question number 25. It's not focused. Okay, focused. In a CCP structure, the slip plane is, which one among this is a slip plane in the CCP? That is FCC. Option C, perfect. Question number 26. If the slip plane is perpendicular to the tensile axis, the resolved shear stress will be maximum 0 equal to the applied stress, half the applied stress. So they are talking about the resolved shear stress. Option B, 0. Whether it's a perpendicular or parallel, in both the cases, it's going to be 0. Very good. 26 is done. Now, it's given that the Schmidt factor is 0.5. What is the ratio of the tau CRSS to the yield strength? 0.5, 0.25, 1, 2. Option A. That is a cos pi and cos theta. This is a Schmidt factor and it will be 0.5. Very good. True and false. Not too much, but now only three questions are left. Let's try to solve them. The Smith's law implies that CRSS is a material constant. True or false? Like for a particular material, it will be fixed. CRSS. That's what they are telling. That Smith's law implies that the CRSS is a material constant. If we talk about the tau CRSS, it will be equal to the yield strength times cos theta cos phi. We know that Smith factor, this will depend upon the angle, the plane at which it's taking place. So either this or this can vary. So what we can say that we know that yield strength is a, what we can say, it's depend upon the directions. It's not the isotropic, it's anisotropic. So this is variable and these are the variables, and tau CRSS is a constant. So for a material, it's a material property. So tau CRSS, the critical resolve shear stress, will be the constant. This is what Smith law has said. So it's not the false, it's a true. Let's move ahead. Yeah, the yield strength sigma y of a single crystal is same in all direction. Yield strength is same in all direction. So just now we discussed that whether it's isotropic or anisotropic. We know that tau CRSS is a constant and theta and phi can change. So what does it mean? That since for this to remain constant and this is changing, so this also has to change. So yield strength in the single crystal is same in all direction. Again, it's a false. It's a false now. It will vary. Yeah, perfect. Because tau CRSS has to be constant. So this A and B are combined Smith law. Okay. Changing the stress axis orientation alter the CRSS. They are telling that if I change theta or phi, anything, my tau CRSS will change. Is it true or false? The answer is option A itself. Right. Option A. We know that tau CRSS is a material constant. Right. Since it's a material constant, it cannot be changed. Whether you change, so see, cos of theta and cos of phi are there. Like the angle between the plane and the direction in which the stress applied, and the direction of concern and the direction in which the stress is applied, times yield strength will be equal to the tau CRSS. This is constant. So even if I change these things, theta or phi, so what will happen? Sigma y will also change in such a manner that if I am increasing this, so it will decrease in such a manner that this will remain constant, or if I am decreasing this, it will increase in such a manner that this will remain constant. So the changing the stress axis orientation alter the CRSS? No, it's false. Okay, so with that we got that it's a true, false and true. Let's move ahead to the next question. Question number 29. Second last. Yeah. So Smith law states that CRSS or yield strength is independent of the stress axis orientation. A. Perfect. CRSS. The yield strength of the single crystal is dash because it depends upon the phi n and phi d. What do you think? A or B? Single crystal. The yield stress of a single crystal is isotropic or anisotropic? Anisotropic means it depend upon the directions. Isotropic means it's same in all the direction. So whether the yield strength yield stress is same in all the direction or it's different in all the direction when we talk about the single crystal. We know we just now discussed that it will be different because tau CRSS is the one which is constant. So sigma y will change. It is an anisotropic. Option B. Let's move ahead. To maintain tau CRSS constant, an increase in the Schmidt factor required the dash in the sigma pi. Schmidt factor is cos pi cos theta. So this is the yield strength. This is tau CRSS. We know that this is constant. Now they are telling that to maintain tau CRSS constant, an increase in Schmidt factor, that is this. So this is increasing. Will require dash in the sigma y, whether sigma y should increase or it should decrease. This is the question. So yeah, very good, it should decrease, or else they both will increase and the tau CRSS will be in the problem. So it's option B is the right answer. Very good. Now let's move to the last final questions. This question is numerical type. You can find the similar type of question in few gate exam and also in the assignment of this particular week. Let's try to solve them. Consider a metal single crystal oriented such that the normal of the slip plane and the slip direction are at the angle of 60 to 35 respectively with the tensile axis. So let us say this is our single crystal. This is our tensile axis. Let's say this is my plane. This is the normal to the plane. And let's say this is my slip direction. First we'll try to understand the question. So the plane angle is 60 and the direction angle is 35. So this is 60. This is 35. If CRSS, that is tau CRSS, is given to us, it's 6.2 MPa. Will an applied stress of 12 MPa, this is 12 MPa is applied, cause a single crystal to yield? So will the deformation will take place? That will only happen if the resolved shear stress in this particular plane, in this particular direction, is greater than this. So we have to find that the tau CRSS is less than RSS, resolved shear stress. The how much is applied, if it is greater than the tau CRSS, then the yielding will occur. Yield will take place. While if the critical resolved shear stress is more than the what is applied, then the yielding will not take place. So let's try to find the resolved shear stress. It is given that the applied force sigma times Schmidt factor cos theta cos pi. Things are given to us. This is 12 MPa. Cos theta cos of 60, cos 5 cos of 35, theta and 35. So 60 and 35. Now we can solve it. Twelve multiplied by cos of 60 multiplied by cos of 35. So what we are getting is, we are getting that the value is 4.915 MPa. Now this value is less than this value, the tau CRSS 4.915 is less than 6.2 CRSS. So our material is safe. So you can apply this particular load to the single crystal and it's not going to deform. So what's stating that? Okay, so we concluded that yielding will not take place. This is our answer. If not, okay, yeah, we concluded that it won't take place. If not, what stress will be required, will be necessary. So they are telling that, okay, what stress will be necessary to cause this particular yielding to take place. So let's go ahead. So we know that tau CRSS will be equal to the yield strength multiplied by the Smith factor. Okay, it's the right answer is 15.13. Okay, I will also just have a look. Sigma y will be equal to tau CRSS divided by cos of 60 cos of 35, which is given as 6.2 divided by cos 30 cos of 6 cos of 60 cos of 35. Yeah, perfect. Very good. So we got that the yielding will take place when the our yield strength, the applied stress, is greater than the 15.13 MPa. So if this one, this sigma applied, which was 12 right now, if it is more than or equal to 15.13 MPa, then yielding will take place. So with that, we have solved all the questions that I have planned for this particular week. So you'll find the similar type of questions in the assignment. Like one question is similar to this. So let's just quickly have a look on all the questions. Here we talk about the tau CRSS and all, the same thing over here. The Smith factor we talk about, then we talk about the resolve shear stress, and close packing. In the close pack structure, we talk about the slip lines we talk when deformation will take place, and how the loading and unloading cycle will behave. Then few questions on the strength of the like the tensile stress things, strength of the materials. We talk about the hardenability concept. These are the few match the following pair, like how the alloying will affect the TTT curve. Same goes over here also. Same. Then we talk about A3 and ACM line. Under the what, like how the hypo and hypoeutectoid will differ from the plane. And then we talk about the mark benching, mark tempering, those stuff. Similar, like from the same set line, this type of question has been done. Again, what is mark quenching, mark tempering, why it is required, that thing has we discussed. The volume change, we discussed that the stress produced within the residual stresses produced during when the quenching will take place. Then we talk about the tempering of the martensite, why it is carried out, and what result is produced. On the similar line, we have done this also. Perlite, bainite, and martensite transformation. So more or less, we talk about the heat treatment in the first section of our discussion, today's discussion. Composition change will not occur in the martensite. And here are the few again, similar type of question, and the structure of the austenite, ferrite, and martensite. These are the list of the content that has been covered in this particular week. So as here. So with that, we have concluded our week 10. If there is any doubt in this particular entire discussion of us, and also like any assignment type questions you want to discuss, or if there is anything like the thing that has been covered in the class and you've not understood anything, question is there, please let me know, or else we'll wind up today's session. Okay, That's great, Ramiri. So with that, we have concluded our today's doubt solving session of week 10. 2 more weeks are left, and let's meet again in the upcoming week, same time, Saturday. Okay, bye bye. Have a nice week.